Hey everyone, welcome. Today, we're tackling Leetcode problem 2563. Count the number of fair pairs. It sounds simple enough, but like many Leetcode problems, there's a catch if we want to be efficient. We'll walk through it step by step, starting with the basics, and then figuring out a smarter way to solve it. Ready? Let's dive in. Okay, so what's the goal here? We're given a list of numbers, called nums. We're also given two boundary numbers, lower and upper. Our job is to find out how many pairs of numbers from the list meet a specific condition. For any two numbers in the list, let's say at positions, and they form a fair pair if two things are true. First, must come before in the list. Second, when you add the two numbers together, their sum must be at least the lower bound, and at most the upper bound. So the sum has to fall within that range, including the boundaries. We need to count how many such pairs exist in the whole list. The list can be pretty big, maybe up to 100,000 numbers, and the numbers themselves can be quite large or small. That gives us a hint that just checking every single possible pair might be too slow. Let's look at this example. Our numbers are 0, 1, 7, 4, 4, 5. The lower bound is 3, and the upper bound is 6. We need pairs, I, j, where I comes before j, and the sum is between 3 and 6. Okay, let's check some pairs. How about index 0, value 0, and index 1, value 1? Sum is 1, too small. How about index 0, value 0, and index 3, value 4? Sum is 4. Is 4 between 3 and 6? Yes, so 0, 3 is a fair pair. What about index 0, value 0, and index 4, value 4? Sum is 4 again. Yep, that works too. 0, 4 is fair. Index 0, value 0, and index 5, value 5. Sum is 5. That's also in range. 0, 5 is fair. Now let's try starting with index 1, value 1. Index 1, value 1, and index 3, value 4. Sum is 5. Good. 1, 3 is fair. Index 1, value 1, and index 4, value 4. Sum is 5. Good again. 1, 4 is fair. Index 1, value 1, and index 5, value 5. Sum is 6. That's exactly the upper bound, so it counts. 1, 5 is fair. If we keep checking, like 2, 3, which is 7 plus 4 equals 11, that's too big. It turns out those 6 pairs we found are the only ones. So the answer is 6. See the process? So the most straightforward idea, the brute force way, is just what we did manually in the example, but systematically. We could use nested loops. The outer loop picks an index starting from the beginning. The inner loop picks an index starting from I plus 1 all the way to the end. For each pair, I, P, C, J, we calculate the sum of the numbers at those positions and check if it falls within our lower and upper bounds. If it does, we increment a counter. Easy enough to code, right? But remember that constraint? The list size can be up to 100,000. If we have nested loops, the number of pairs we check is roughly n times n, or n squared. If n is 100,000, n squared is 10 billion. That's way too many operations. We'll definitely hit a time limit. We need a more clever approach. Okay, how can we speed this up? A really common trick when dealing with pairs or sums in arrays is sorting. Let's sort the input array nums first. Why does this help? Well, if the array is sorted, as we look at numbers for our potential nums, they'll be in increasing order. Now, think about it. For a specific number nums, we're looking for numbers nums, where j is after I, that fit into a specific range. That range is determined by our original lower and upper bounds, adjusted by nums. Specifically, nums needs to be between lower minus nums and upper minus nums. Since the array is sorted, all the potential nums that satisfy this condition will be grouped together in a contiguous block after nums. Finding how many numbers fall into a range in a sorted array sounds like something we can do faster than checking one by one. Here's a neat trick to handle the range. Lower, upper. Instead of directly counting pairs whose sum is within that range, let's rephrase the problem. The number of pairs with a sum between lower and upper, inclusive, is equal to the total number of pairs with a sum less than or equal to upper, minus the total number of pairs with a sum less than lower. Does that make sense? We count all pairs up to the upper limit, and then we subtract the ones that are below the lower limit. Finding pairs with a sum less than or equal to a specific target value. That's a classic problem we can solve efficiently, using the two pointers technique on our sorted array. Okay, Let's focus on how to count pairs. In tuple j, where I is less than j, and their sum is less than or equal to some target value, we'll use our sorted array nums. We set up 2 pointers, left starting at the very beginning, index 0, and right starting at the very end, index n1. Now we loop as long as left is still to the left of right. Inside the loop, we check the sum of the numbers at the left and right pointers. If this sum is less than or equal to our target, great. This means that the number at left can successfully pair up not only with the number at right, but also with all the numbers between left and right, because they are even smaller than nums right. How many such numbers are there? It's right minus left. So, we add right left to our total count. Since we've found all pairs for this nums left, we move the left pointer one step to the right to consider the next number. Boot. What if the sum nums, left plus nums right, was greater than the target? Then, the sum is too big. To make the sum smaller, we need to decrease the larger number, so we move the right pointer one step to the left. We keep doing this until left meets or passes right. The final count is our answer for count underscore less underscore equal. Alright, here's the Python code putting it all together. Don't worry if it looks like a lot at first glance. We'll break down the key parts. You can see the main function count fair pairs, and inside it we have that helper function count underscore less underscore equal that we just discussed. The main function first sorts the numbers, then calls the helper function twice, once for the upper bound and once for lower minus 1, and subtracts the results. That gives us the final count of fair pairs. First things first, inside our main function count fair pairs, we absolutely need to sort the input list nums. This is crucial for the two-pointer approach to work correctly. We just use the built-in sort method. We also grab the length of the list and store it, usually in a variable like n, just for convenience. Now here's that helper function count underscore less underscore equal. It takes the target sum as input. Inside we initialize our pair underscore count to 0, set up the left pointer at the start, index 0, and the right pointer at the end, index n1. The while loop runs as long as left is before right. Inside we check the sum. If it's less than or equal to the target, we add the difference right left to our count and move left forward. Otherwise, if the sum is too big, we move right backward. Finally, after the loop finishes, we return the total pair underscore count we found. And the last step in the main function is to put it all together. We call our count underscore less underscore equal helper function once, with the original upper bound. This tells us how many pairs have a sum less than or equal to upper. Then, we call it again, but this time with lower minus 1 as the target. This tells us how many pairs have a sum strictly less than lower. Subtracting the second result from the first gives us exactly the number of pairs whose sum is between lower and upper, inclusive. We store this final result in count and return it. That's it. So how much better is this optimized approach compared to the n-squared brute force? Let's look at the steps. First, we sort the array. Most standard sorting algorithms take about n log n time, where n is the number of elements. Then, we call our count underscore less underscore equal function twice. Each call uses the two-pointer method, which goes through the array roughly once. That's order n time for each call. So the total time complexity is dominated by the sorting step. It's big O of n log n. This is much faster than n squared when n is large. What about memory? Well, the sorting might use some extra space, depending on the specific algorithm used, maybe order n, or order log n. Other than that, we're just using a few variables for pointers and counts, which is constant extra space, or order 1. So the space complexity is mainly determined by the sort. Much better overall. Okay, let's quickly recap the main points. The problem asked us to count pairs within a specific sum range. Trying all pairs directly is usually too slow, around n-squared time. The key insight was to sort the array first. This allows us to use more efficient techniques. We saw that finding pairs in the range, lower-upper, is equivalent to finding pairs less than or equal to upper, and subtracting pairs less than or equal to lower minus 1. And finally, we learned how to count pairs with a sum less than or equal to a target value efficiently using the two-pointer technique on the sorted array, which takes only order n time after the initial sort. Combining these ideas gives us a much faster n log n solution. Hope that breakdown made sense and helped you understand how to approach this problem. If you found this useful, please give the video a thumbs up, and maybe subscribe for more Leetcode explanations. If you have any questions or alternative ideas, feel free to drop them in the comments below. And hey, if you're feeling extra supportive, the Boba Fund is always appreciated. Thanks for watching, keep practicing, and I'll see you in the next one. Happy coding!